So today we are going to learn an important topic, that is Hückel's molecular orbital theory of conjugated ions. You know what are conjugated ions? In conjugated ions, you can see the double bonds separated by the single bonds like this. Okay, so these are conjugated ions, and Hückel molecular orbital theory describes on the bonding of these conjugated ions. Okay, and this is an empirical method used for the planar conjugated ions. It's very important. It is for the planar conjugated ions. So this is very important. Planar conjugated ions. Okay, and the method is based on the following assumptions, and we will see what are these assumptions. The pi electrons in a conjugated molecule do not interact with the sigma electrons, because in a molecule you can see not only the pi electrons but the sigma electrons as well. Okay, but there is no interaction between the interaction between the pi electrons and sigma electrons in the molecule. And this Hückel molecular orbital theory specifically applies for only the pi electrons, not for the sigma electrons. Okay, that is the first assumption. The Hückel's molecular orbital theory applies only to the pi electrons, and these pi electrons are not interacted by the sigma electrons. And the second assumption is that the total wave function is a product of the one electron functions called Hückel molecular orbitals. Okay, and that is the total wave function for all the pi system, that is psi pi is equal to psi 1 1, psi 1 bar 2, psi 2 3, psi 2 bar 4, etc. to psi n by 2 n minus 1, psi n by 2 n bar. Okay, I will explain what are these. Here in this expression, each psi I means psi 1, psi 2, psi 3, etc. to psi n by 2. Each psi I is a Hückel molecular orbital. Okay, and the numbers inside this bracket, they denote the electrons. Means this is electron 1, this is electron 2, electron 3, electron 4, etc. to electron n. Means we are describing the wave function of an n electron system here, and the numbers inside this bracket represents the electron number. Okay, and the line over this psi denotes the beta spin of the electron, and if there is no bar or line, it means that the electron is in the alpha spin. Okay, that's what all the terms here explains. So the total molecular orbital wave function psi pi is equal to psi 1 1, psi 1 bar 2. It means that in the same molecular orbital, same Hückel molecular orbital psi 1, there are two electrons, electron 1 and electron 2. Out of that, the electron 1 has alpha spin and electron 2 has beta spin. Like that, the second Hückel molecular orbital, that is psi 2, has two electrons, that is electron 3 and electron 4. Out of that, electron 3 has alpha spin and electron 4 has beta spin, like that. And you can see here that we have the n by 2 Hückel molecular orbitals. This is because the system has n electrons. Suppose the n electron is an odd even number. So in order to accommodate the n electrons, we need only n by 2 Hückel molecular orbital, because each orbital can accommodate 2 electrons. Okay, that's how this this function is constructed. And now the total energy is the sum of the electron energies of the Hückel molecular orbitals. Means if E1 is the energy corresponding to the Hückel molecular orbital psi 1, and E2 is the energy corresponding to the Hückel molecular orbital psi 2, and En is the energy corresponding to the HMO psi n, then the total energy is equal to N1 E1 plus N2 E2 plus Nn En, where N1 is the number of electrons in psi 1, N2 is the number of electrons in psi 2, Nn is the number of electrons in psi n, etc. Okay, so Ei is the energy of the psi HMO psi I. Okay, and what is the maximum value of N1, N2, N3, etc.? The Ni, any Ni value, can have only three values: 1, 2, or 0. If it is 0, it means that orbital is not occupied by any electron. If it is 1, it means that orbital is occupied by one electron. If it is 2, the orbital is fully occupied, means the maximum strength of electron or maximum number of electrons in an orbital is 2. Okay, so Ni can be 1, 2, or 0, corresponding to the number of electrons in each psi I. Okay, if the number of electrons in the psi 1 is 1, then you have to write 1 into E1. Okay, if the number of electrons in the psi 2 is 2, then you have to write 2 into E2 plus the number of electrons in the nth Hückel molecular orbital is 0, then you have to write 0 into En, like that. Okay, so that is how the energy of the total, the expression for the total energy can be written. And now psi I is an approximate solution of the Schrodinger wave equation. H cap I psi I is equal to E I psi I. Psi I, as you know, is the Hückel molecular orbital, ith Hückel molecular orbital, and corresponding to that there is an eigenvalue equation or a Schrodinger equation, that is H cap I psi I is equal to E I psi I. Okay. However, you have to remember that even if the psi I and Ei are included as the eigenfunction and eigenvalue of the Schrodinger wave equation, the Hamiltonian is not specified, and the Schrodinger wave equation is not solved in this Hückel molecular orbital method. Okay, that you have to remember. And the third assumption is that each Hückel molecular orbital, that is psi I, is a linear combination of all the carbon 2pz atomic orbitals. Okay, means the pz orbitals are the pz orbitals you have to take, and each pz orbital in the carbon is an atomic orbital, and then you take the linear combination of all the pz atomic orbitals. Okay, and you already know that we are applying the Hückel molecular orbital theory for a molecule which is planar, and these pz orbitals are perpendicular to this molecular plane. You can take the molecular plane as xy, then the pz orbital will be perpendicular to the xy plane. Okay, so you take the pz orbitals of all the carbons which are included in the conjugation, and then you can take the linear combination of all these pz orbitals, and that combination gives a Hückel molecular orbital. So each Hückel molecular orbital is constructed by the linear combination of the p's atomic orbitals of the carbon. So any Hückel molecular orbital psi I can be written as AI1P1 plus AI2P2 plus AINPN, or you can write it like sigma r is equal to 1 to n AIRPR. Here the PR is the 2pz atomic orbital of the rth carbon atom, and the AIR is the coefficient in the linear combination. Okay, so if you have 5 or 6 carbon atoms which are there in the conjugation, then you have to take the pz atomic orbitals of all the 6 carbon atoms, and then you take the linear combination of the pz orbitals of all the 6 carbon atoms and make a particular Hückel molecular orbital. Okay, that's the third assumption. And the energy of the Hückel molecular orbital, energy of the Hückel molecular orbital psi I, can be calculated as Ei is equal to integral psi I h cap psi I d tau divided by integral psi I square d tau, and we assume that psi I is real. Okay, otherwise we have to write psi psi star, like that. We assume that psi is real, that's why it is written here integral psi I square d tau, like that. Okay, so this will give the energy. You already know this energy. This is the expression for the expectation value. Okay, so if you know the psi I, then you can find out the expectation value corresponding to that psi I by this expression. Ei is equal to integral psi I h cap psi I d tau divided by integral psi I square d tau. And now we have the expression for psi I as a linear combination. And now we know how to get the expectation value corresponding to each psi I, and this leads to the variation treatments, and this variation treatment leads to n secular equations. Okay, and you know how to write these secular equations. We already learned this in the variation theorem. So these n secular equations will be A1 H11 minus E S11 plus A2 H12 minus E S12 plus etc. plus an H1n minus E S1n, that is equal to 0. That is the first secular equation. The second circular equation can be written like A1 H21 minus ES21 plus A2 H22 minus ES22 plus etc. plus an H2n minus ES2n, that is equal to 0. And the nth circular equation can be written as an Hn1 minus ESN1 plus A2HN2 minus ESN2 plus etc. plus an HNN minus ESNN, that is equal to 0. Okay, here it is very easy to write this. Here you have to write the coefficients A1, A2, A3 etc. to an in all the equations A1, A2, A3 etc. to an, A1, A2, A3 etc. to an. That's there in all the equations. But what you have to consider here is the expression which is inside the bracket. Here H11, ES11, okay, 1 1 1 1. This shows the row and column integers, means the first row, first column. Here it comes as first row, second column. That is why it is 1 2. Here it comes here, it is first row, nth column. That is why it is H1n. And when it comes to the second equation, that is second row and first column, that's why it is 2 1. Then second row, second column, that is it is 2 2. And when we come to here, it is nth row, nth column, that is why it is n. So it is very easy to write these circular equations. Okay, and corresponding to these circular equations, there will be a circular determinant as well. In order to get the circular determinant, we are taking the coefficients of A1, A2, A2, A3, etc. to an from all the equations and write it as a determinant. So the circular equation is determinant H11 minus ES11, H12 minus ES12, etc. to H1 and ES1n. And the second row of the determinant is H21 minus ES21, H22 minus ES22, etc. to H2n minus ES2n, and etc. When we reach the nth row of the determinant, then it will be Hn1 minus ESN1, Hn2 minus ESN2, etc. to Hnn minus ESNn, and this determinant will be equal to 0. That's why then we call this as a circular determinant. Okay, and here you already know what are H11, H12, S11, S12, etc. And just to remind you, I will write it here, and that is Hij is equal to integral Pi H cap Pj d tau, and Sij is equal to integral Pi Pj d tau. Okay, and at this stage, the Hückel molecular orbital theory puts forward the following drastic approximations. Okay, these approximations are: all HRR are equal. All HRR are equal means H11 is equal to H22, and that is again equal to H33, and that is again equal to HNN. Okay, so 1 1 1 2 2 3 3 etc. Okay, so all HRRs are equal, and let's say it's equal to alpha. And if the earth and th carbon atoms are directly bonded, okay, it's very important. If the earth and th carbon atoms are directly bonded, then all the HRRs are identical and it is equal to beta. Let's say beta, okay, means 1 and 2 are directly bonded carbon atoms. 2 and 3 are directly bonded carbon atoms. 3 and 4 are directly bonded carbon atoms. So corresponding to these directly bonded carbon atoms, if we are taking the H functions, that is H12, H23, H34, etc., all these functions will be equal, and that functions will be equal to beta, let's say. Okay, that is the second drastic approximation. And if the earth and th carbon atoms are not directly bonded, if they are not directly bonded, then HRS is equal to 0. It means H24 is equal to 0, or H14 is equal to 0, H13 is equal to 0, because they are not directly bonded in a linearly conjugated molecule. Okay, so HRS will be 0 if earth and th carbon atoms are not directly bonded. And now the value of alpha and beta are used as experimental data. We depend upon the experiment to fill the value for the alpha and beta. And all SRR are equal to 1, means S11 is equal to S22 is equal to S33, etc. is equal to SNN, that is equal to 1. But you have to remember that all the SRs are 0 if R and S are different, means S13 is equal to S35, etc. is equal to 0. Okay. So these are some of the drastic approximations that we have to consider. Let us remind once again. Let's consider these drastic approximations once again. All HR are equal to alpha, means H11, H22, H33, etc. HNN is equal to alpha, and all HRs, if R and S are the directly bonded carbon atoms, are equal to beta. Okay, means H12, H23, H34, etc. is equal to beta, and HRs is equal to 0 if the R and S carbon atoms are not directly bonded. Okay, and the value of alpha and beta are used as experimental data, and all SR are equal to RR is equal to 1, means S11 is equal to S22 is equal to S33 is equal to 1, but all SRs are 0 if S and R and S are not identical. Okay, means S13 is equal to S35, etc. is equal to 0. Okay, thus for a linear conjugated chain, the secular determinant become the secular determinant that we have already written above. This secular determinant, that secular determinant becomes alpha minus E beta 0 0 0 0. Okay, let's consider why. Let's see how it became alpha minus beta. See here, H11 is equal to alpha minus E into S11. S11 is equal to 1. So alpha minus E. This is alpha minus E. And what about the other one? H12. H12 is equal to 0. Okay. And then no, H12 is equal to beta because 1 and 2 are directly bonded carbon atoms. So H12 is equal to beta, and S12 is equal to 0. So this becomes beta minus 0, that is equal to beta. So this is alpha minus E, this is beta, and if you are considering the next one, it will be H13, and H13, 1 and 3 are not directly bonded. So H13 will be equal to 0. And S13 is also equal to 0. So the next element will be 0. So if you are considering any other element after that, it will be 0. So the first row will be alpha minus E beta. Okay, then 0 0 0 0 0 etc. to 0. That is what it is written here. Alpha minus E beta 0 0 0 0 0. Okay, if you are considering the second row, the second row is H21 minus ES21. H21, 2 and 1 are directly bonded carbon atoms. Therefore, H21 will be beta minus ES21. S21 is equal to 0. Okay, so this is beta. And what about this one? H22. H22 is equal to alpha because it is like HRR. Okay, this is alpha minus ESRR. ESRR is equal to 1. So this is alpha minus E. Okay, and if you are considering the next element, it is H23. H23 is equal to H23 is equal to beta. Okay, minus S23. S23 is equal to 0. So it will be beta. So we get beta, alpha minus E, beta, etc. If you are considering any other element, then it will be equal to 0. So the second row will be beta, alpha minus E, beta 0 0 0 0 etc. to 0. The third element will be 0, beta, alpha minus E, beta 0 0 0 to 0, and etc. etc. If we are reaching the last row, then we can see that all the first elements will be 0, and then we come to the second last element, it will be beta, and then the final element will be alpha minus E. So this determinant is equal to 0. Okay, it is very easy to write this determinant. You can see that the first element is alpha minus E. Okay, all the diagonal elements here are alpha minus E, and if there is an alpha minus E, left and right will be beta. Okay, and there is no left element here, but there is a right element here, so that the right element should be beta here. Okay, all other elements are 0. And here you can see that the alpha minus z is here, and right and left should be beta. Fortunately, this element has right and left elements, so this is beta, this is beta. All other elements are 0. And alpha minus z comes here. Left and right are beta, so beta is put here, another beta is put here. It is not written, but there is a beta here. Okay, and 0, 0, 0. And when we are coming to the last, alpha minus zeta is here, the last element. So there is no right element here, so we don't need to consider here. Or there is left element, that left element will be equal to beta. So this is how you can write this determinant. Now the determinant can be still made simpler by putting alpha minus e by beta is equal to x. What we are going to write, what we are going to do is we are going to divide the entire elements in this determinant with beta. Okay, let me divide this alpha minus e by beta, beta by beta, 0 by beta, etc. Okay, I am dividing the entire element with beta, and then I have to divide the right hand side also with beta. 0 by beta is equal to 0. So I can write it like this entire determinant divided by beta is equal to 0. It means that alpha minus e divided by beta. So let me put alpha minus e divided by beta as x. So the first element will be x, and beta by beta is equal to 1. So the second element is 1. Okay, then 0, 0, 0, 0. And what about the next row? Beta by beta is equal to 1. That is what is written here. And alpha minus e by beta is equal to x. So that is written there. So beta minus beta divided by beta is equal to 1. So that is written there. Okay, then the next elements are 0. Like that we can write the third like 0, 1, x, 1, etc. 0, 0, 0. And finally we will reach the nth element, and there we will have 1 and x here, the second last and the last element. And that determinant is equal to 0. Okay. So we have made the determinant simpler. And now we can look at some features of this determinant. Here we can see that all the x appears in the diagonal, right? Principal diagonal. All the x appears on the principal diagonal. And 1 appears on the positions corresponding to bonded carbon atom. You can see the position of this 1. This is the position, first row, second column. So it is 1, 2. 1 and 2 are bonded carbon atoms. So in the place of the bonded carbon atom, you can see 1 here. And what about this one? This is second row, first column, 2 and 1. They are bonded carbon atoms. So you have 1 here. This is the position of the second row and the third column, 2 and 3. They are bonded carbon atoms. So we have 1 here. Like that, wherever you have the bonded carbon atoms, okay, the 1 appears on the positions corresponding to the bonded carbon atoms, and 0 appears where there is no bond. So you can consider this 0 here. This is a position 1, 3, and there is no bond between 1 and 3. Therefore, this is equal to 0. Okay, if you are considering here, this is 1 n, and then there is no bond between 1 and n, so that is equal to 0, like that. Okay, if you are considering here, this is 3, 1, there is no bond between 3 and 1, so this is 0, like that. Okay, so 0 appears where there are no bonds between the carbon atoms of the conjugated system. So the Hückel determinant can be written looking at the structure of the hydrocarbon as follows. You sketch the framework of the molecule. That's what we have to write. First, sketch the framework of the molecule. For example, if you have butadiene, so this is butadiene. So if you want to sketch, if you want to write the determinant corresponding to the butadiene, you have to sketch the framework of the molecule. Means C1, C2, C3, C4. That is a framework. Okay, C1, C2, C3, C4. We just need to show where the carbon atoms are bonded, which carbon atoms are bonded together. So C1 and C2 are bonded, C2, C3 bonded, C3, C4 bonded. 3 bonds are there. Okay, sketch the framework of the molecule. Now the number of the carbon atoms. Now the number of the carbon atoms. The number of the carbon atoms is 1, 2, 3. That is why it is written C1, C2, C3, C4, etc. Okay, and now create the determinant by filling X on the principal diagonal, 1 in positions where the indices correspond to the bonded carbon atoms and 0 everywhere else. Okay, that's what we have to write. We have to make the determinant, fill the principal diagonal with the X, and we have to look at the positions corresponding to the bonded carbon atoms. Means wherever you see the indices means row and column numbers. Okay, so wherever the indices are corresponding to the bonded carbon atoms, you put 1 there. And if you see that the indices are not corresponding to the bonded carbon atoms, then you put 0 there. Okay, so this is how you construct the determinant. And this determinant, when you construct this determinant, and you can check whether this determinant is correct or not by looking at the symmetry. The determinant must be symmetric with respect to the reflection through the principal diagonal. Okay, so if you are keeping a mirror along the principal diagonal, and you have to get the mirror image of the one side, the mirror image of the elements, the arrangement of elements in one side of the mirror should be the arrangement of elements in the other side of the mirror. So there should be mirror images to each other. So you can check whether the determinant that you have written is correct or not by looking at the symmetry of the determinant. Okay. Now we can work out some examples. The first example is butadiene. So the carbon skeleton is C1, C2, C3, C4. The carbons are numbered here, and then you have to write the row numbers. These are the row numbers, and then you have to write the column numbers here also. Since there are 4 carbon atoms, you will have 4 rows and 4 columns. So first we have to fill all the diagonal elements. So we fill X, 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 and X. These are the diagonal elements. Okay. And now we have to look at the positions where indices are corresponding to the bonded carbon atoms. So this is a position here. This is the position corresponding to 1, 2. 1 and 2 are the bonded carbon atoms. So you have to fill 1 there. And when you are coming here, it is the indices here are 1, 3, first row, third column. 1 and 3 are not bonded carbon atoms. See, there is no bond between 1 and 3. So you have to put 0 there. So 0, 0. And like that, you can fill the other elements, the space for other elements. Here it is 1, 2, so it is 1. It is 2, 3, so it is 1. 2 and 3 are bonded. The 3, 2 and 4 are not bonded, so it is 0. Like that, we can write 0, 1, x1, 0, 0, 1, x. Okay, so this is the Hückel determinant corresponding to 1, 3 butadiene. And then now let us consider the example. Oh, we can consider whether it is symmetric or not. If you are making a mirror image here, so let me put a mirror here along the principal diagonal. You can see how the images are coming. Okay, so this 1 will be reflected here, and this 0 will be reflected here, and this 0 and 1 will be reflected as 1 and 0 like this, right? This will be reflected here, and 0, 0, 1 is reflected like this. 1, 0, 0, it is reflected like this. So this is reflected here. So it is symmetrical. Okay, no problem. Now let us look at the example of benzene. This is more tricky. Okay, so this is a cyclic one. This is not linear. So you should be very careful. First, let us draw the skeleton. C1, C2, C3, C4, C5, C6. And you can see that C1, C2 are connected, C2, C3 connected, C4, C3, C4, C4, C5, C5, C6, they are connected. And in addition to that, C6 and C1 are connected. Okay, that's why it's a ring. C6 and C1 are connected. So you should be very careful while you are filling the elements of the Hückel determinant. First, we have to write the row and column numbers. These are all row numbers. These are all column numbers. Okay, and then we write X, 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 X through the diagonals, and then we are looking at the other positions. We have to fill the other positions. Here it is 2, 1. Okay, 1, 2. Okay, this is 1, 2. So 1 and 2 are connected. So it is 1. This 1 and 3 is 0. 1 and 4 0. 1 and 5 0, because there are no bonds between these carbon atoms. When it comes to 1 and 6, yes, it is not 0. It is 1, because 1 and 6 are connected. So it should be 1 here. Okay, so when you come to fill up here, 2 and 1 are connected, so it's 1. 2 and 3 are connected, so it's 1. All other elements are 0. Here 2 and 6 are not connected, so it should be 0. Okay, right, like that you can write the other elements also. You can try yourself to write the third row, fourth row, fifth row. Okay, fifth row you can consider like this. Okay, one is here because there is 5 and 4 connection, and if 5 and 6 connection is there, therefore one is here. But when you come to the sixth row, the first element, that is 1 and 6, yes, there's a connection between 1 and 6, so it should be 1. But there is no connection between 2 and 6, so it should be 0. There's no connection between 3 and 6, so it's 0. There's no connection between 4 and 6, so it's 0. But there is a connection between 5 and 6, so it's 1. Okay, so it should be 1. So if you can, this is the Hückel determinant corresponding to the benzene. Now you can construct them. You can put a mirror there. Let me put a mirror there. Okay, through the principal diagonal. Okay, this is a mirror, and you can check the mirror images. Okay, all the x are coming in this line. Even if you are seeing that x is a little bit positioned away from the line, that is just because of my inability to write the x in the correct positions, but you have to assume that all the x are in the line. Okay, so this line represents the cross section of the mirror. So if you are looking at the mirror images, okay, so 1 is reflected here, 0 1 is reflected as 1 0 here, 0 0 1 reflected as 1 0 0 here, 0 0 0 1 are reflected as 1 0 0 0 here, and 1 0 0 0 1, that is reflected as 1 0 0 0 1 here. So it's symmetric. So with respect to the mirror image which is drawn through the principal diagonal, this determinant is symmetric. So determinant is correct. Okay. And now we are coming to the seventh assumption, the Hückel molecular orbital energy levels. Okay, expansion of the n by n determinant leads to a polynomial of nth degree in x. Our determinant is n by n determinant, so we will get a polynomial of x, and the degree of the polynomial x, the degree of this polynomial will be nth degree. So this is going to give n roots of x. If you are solving this determinant, you will get n roots of x, that is x1, x2, x3, etc. to xn. N values of x will be obtained. And you already know that x is equal to alpha minus e divided by beta. Okay, we already know this. And from this, if we are getting the expression for e, then e is equal to alpha minus x beta. It indicates that for each root of x, for each value of x, for say for example xj, there will be a corresponding e, because e depends upon x. So for each value of x, you will get each value of e. So the ej, the value ej will depend upon xj. So ej is equal to alpha minus xj into beta. So what you have to understand from here, that is, there will be n energy levels corresponding to n Hückel molecular orbitals. Okay, if there are n carbon atoms, you will get n by n determinant, and corresponding to n by n determinant, there will be n solutions of x, and corresponding to the n solutions of x, you will get n values of Vj. It means that there will be n Hückel molecular orbital corresponding to n values of energy. Okay, there will be n energy levels corresponding to n Hückel molecular orbitals. Now, alpha is equal to integral pi h cap pi d tau. Okay, and that is equal to the energy of the electron in the ith pz atomic orbital, and alpha will be negative. Alpha will be negative to the energy of a free electron. Okay, when you are comparing to the energy of the free electron, alpha will be negative. That is the energy of the electron in the ith pz atomic orbital. That is, then beta is equal to integral pi h cap pj, that is beta. Okay, and I and j are bonded carbon atoms. Okay, when I and j are bonded carbon, then only we consider it as beta. If they are not bonded, then it is 0. So beta is equal to integral pi h cap pj d tau, where I and j are bonded carbon atoms. So it corresponds to the energy of the electron in a bond. So what is alpha? Alpha is the energy of the electron in the ith pz atomic orbital, but beta is the energy of the electron in the bond. So beta will also be negative. Alpha is in the atomic orbital, so its energy will be less than the energy of the free electron, so it's negative. Beta will be negative because it's also a part of the bond, so beta will be negative. So xj is equal to positive, negative, or 0. Okay, xj can be negative, positive, or 0. So now we are considering what will happen if if xj is a negative, for negative root xj. So if xj is less than 0, then ej is less than alpha, right? If xj is less than 0, then ej is less than alpha. Okay, that corresponds to the bonding level. We can see that what is the relation between ej and xj. See, ej is equal to alpha minus xj into beta. Here alpha is already negative, beta is already negative. So if xj is also negative, then it means that ej is if ej is less than alpha. Okay, because this will be this is minus xj into beta. Xj is negative, beta is also negative, so negative into negative, this will be a positive quantity. So this positive quantity, when comes here, it will be ej plus a positive quantity. It means that then ej plus a positive quantity is equal to alpha. It means that ej is less than alpha. So when xj is negative, it means that ej is less than alpha. If ej is less than alpha, what does it mean? It corresponds to the bonding level. Alpha is the energy corresponding to the electron in the pz atomic orbital, right? If ej is less than that, then it corresponds to the bonding level, means energy is saved, then it would be in the normal pz atomic orbital. And for positive root, means if xj is equal to 0, then it will, the reverse will be the case. Then ej will be greater than alpha. It means that it corresponds to antibonding, means even if xj is equal to 0, then an energy level is reached. The Hückel molecular orbital will have an energy, and Hückel's molecular orbital's energy will be greater than the energy of the atomic orbital. So when the Hückel molecular orbital is formed, no energy is saved. It means that it is an anti-bonding situation. Okay, and for 0 root, means when xj is equal to 0, then ej will be equal to alpha. It means that the Hückel molecular orbital will have the same energy of the atomic orbital. It means that there is no gain, at the same time there is no pain, means nothing happens, means it is a non-bonding level. Okay, so when xj is equal to 0, it corresponds to the non-bonding level. So ej is the energy of the here ej is the energy of the jth Hückel molecular orbital. Okay, so corresponding to different values of different roots of xj, we have different bonding situations like bonding level, anti-bonding level, and non-bonding level. Now let's look at the coefficients. By substituting the values of V in the n simultaneous secular equations, the relative values of coefficients are obtained. Okay, we know this already. We are substituting the energy in the secular equations. Then it will give the relative values of coefficients. Okay, A1, A2, etc. And absolute values are obtained by applying the normalization condition. We have already done these steps while learning the variation theorem. Okay, so by normalization step, then we can get the absolute values of the coefficients. The normalization step is nothing but integral I1 P1 plus AI2 P2 plus AI3 P3 plus etc. plus AN Pn, the all square d tau is equal to 1, assuming that the entire linear combination is real, and therefore AI1 square plus AI2 square plus etc. plus AN square is equal to 1. For each value of E, we will get a set of coefficients corresponding to the Hückel molecular orbital. Okay. And the ninth one, for a conjugated system of n carbon atoms, there will be n Hückel molecular orbitals. and the pi electrons in the molecule are filled in the Hückel molecular orbital in the increasing order of energy. Okay, one Hückel molecular orbital can accommodate a maximum of 2 electrons of opposite spins, and these are the assumptions of the Hückel molecular orbital theory. I hope you understood this, and if you have any doubt, you can contact me without any hesitation. And thank you for watching. Stay tuned.